Hi everyone. I want to take some time to go over something called naive Bayes, which is the theoretical underpinning of what we did with the bag of words thing where we just multiplied a bunch of probabilities together. I want to show you there's something a little deeper going on in the background, and it's also going to give us a more general framework to do other kinds of data that aren't just bag of words. So let's just recall Bayes' rule first, but I'm going to think about this in the context of sort of an AI modeling problem, where we want to learn what it is that we're seeing. So here what I say is, okay, this is the class that I'm considering. So for the presidential debates, it could be like, it's really our model. It's like, did Hillary say it? Did Donald say it? So we'll call this the class. This is the observation that we have. Okay. So this is our, let's say, data or observation. So what we really want to know is what is the probability that we had an event from a particular class given that we observed something. Now, we usually model it the other way around. We know what this is. This is called the likelihood. So we usually have the probability, or we're able to model the probability somehow, of seeing a particular observation given a class. So what is the probability, for example, that Clinton said the word Donald? That turns out to be higher than the probability that Trump said the word Donald. Okay, so this is called our likelihood. There's a couple other terms here, though. In Bayes' rule, we end up with this term. This is known as the prior probability of a class. So this is, all else being equal, what's the chance that this class was actually active? So what is the chance that Trump was speaking, or what is the chance that Clinton was speaking if I just go to a random place in the debate? I don't tell you anything about what data I've seen. I'm just saying who's speaking. Okay, so we call this the prior probability. And then there's this term down here, which is what is the probability over all classes of making a particular observation. This is often called evidence. All right, so this is how we think about the Bayesian framework in the context of artificial intelligence machine learning. Okay, so I'm going to jump in and do some more derivations in Jupyter now. Okay, this is going to make it a little easier for me to type a bunch of math. So one thing we notice with this formula, let's say that we're looking for the probability of a particular class. I'll call it C1. So the probability that I have a particular class C1, given that I see some data, is equal to, well, it's the probability of X given C1, so that likelihood, times the probability of C1 over the probability of X. Okay, so I'm just saying, okay, that's what it is for a particular class, right? Well, let's write the same formula but for a different class. So let's say I was looking for class 2. What is the probability of that? One thing I notice here is that they both have this divided by px in the denominator. Like this likelihood is not necessarily the same as this likelihood, and this prior is not necessarily the same as this prior, but they have this shared term. So one thing we do is we define something called the posterior likelihood. Where we just get rid of that term in the denominator because it's not going to change the relative probabilities of these two things. If we just want to know which class is more likely, we can ignore that denominator. And sometimes that denominator is nasty, so it's nice to be able to ignore it. So we could just write something called the likelihood, which I'll call L. So posterior likelihood, C1, or just in general, C, some class C given X is equal to probability of X given C times probability of C, which is proportional to the probability of C given X. Okay. So the likelihood is, whoops, let me get that all looking nice there. The likelihood is proportional to the probability, but it's less work to calculate it. Another thing we'll do sometimes is actually this log posterior likelihood. And it's particularly nice because, so let's say log posterior likelihood. This is particularly nice because of the property of a log. So if we take the log of this thing, the product here actually turns into a sum. So I can write this as the log likelihood, the log posterior likelihood, is equal to the log of the likelihood plus the log of the prior. Okay, so that's it. All right, so what we're going to do in this Bayesian classification framework is we're going to figure out which class maximizes this expression. So the question we have is which class maximizes the log posterior likelihood. All right. So this is it for Bayesian classifiers. So let's try to apply this to our specific model of bag of words. Okay. So here we had the scenario where we were just pulling stuff out of a hat, right? We didn't really care where it happened. And the other assumption that we're making is that every pull of the hat is independent. So if I had 1,000 words, it's really like doing 1,000 independent trials. This is a gross simplification of what's actually going on, right? If I say certain words, I'm much more likely to say other words, right? If I'm somebody who's really all about gun control, I'm probably going to say guns. And if I say guns, then I'm probably going to say control with that, right? It's much more likely, given that I've said guns, that I'll say control. But here we'll just treat them completely independently. So it's quite a simple model. But as one of my advisors used to say, make sure you try the simple thing before you try the more complicated thing. Okay. So let's try this. So let's say that given a model with m words in a dictionary, so given a bag of words model with m words in a dictionary, let's pi be the probability of pulling out the ith word. That's how I get the th there. The ith word in the dictionary. Okay. And let's suppose we have a new string, s, with n words in it. We can consider counting the number of words in each category. So let k I be the number of the ith words in the dictionary. So we say that, all the counts over all the words needs to sum to the number of words in the string. So we say that the sum of I equals 1 to m of ki equals n. Okay, so let's look at that. So I'm saying that, okay, I'm going to count the occurrence of each word. Maybe I say Donald 10 times. Maybe I say guns 20 times. So I add those up as 30, and then there's other words. I add those all up. It's the number of words in the string. Okay. So that's my bag of words model. I'm just trying to count how many words there are. So actually, let me do an example, a simpler one than the debates. But let's suppose our dictionary just has 2 words in it: computer and science. Okay. And let's say that probability of seeing computer, I'll just denote that as PC, and the probability of seeing science is PS. Okay. So let's say now I have a string which is computer, science, science, computer, computer. Okay. So what I would say is there are 3 counts of computer. So I'll say K1 is equal to 3, and then K2 is equal to 2. But if I was just going to look at this word by word, I would say that the probability of S, or the likelihood, so the probability of S given this model, so this is a particular class once I assign these probabilities. So the probability of the string given this model is going to be PC, so first word's computer, times, well, the next word's science, that's PS, times another science, times computer, times computer, times computer. Okay, so that's my probability, which if I just combine like terms, I'll end up getting PS squared times PC cubed. Okay. Now this is not the only string that could have given this probability, right? There are other strings. If I say you've got 3 computers and 2 sciences, well, there's other ways I can do that, right? I can say science, science, computer, computer, computer. I can say science, computer, science, computer, computer. There's a bunch of different ways I can do this. And they all have the same probability, and they also all fall under this category. It's like I've pulled out 3 computers, I've pulled out 2 sciences, and I want to consider those all to kind of be the same possibility. I want to model all of those as the outcome here. So what this leads to actually is something called the multinomial distribution. Okay. So let's pause for a second, and we'll go to the next page, and I'll talk about the multinomial distribution.